electromagnetic radiation is the emission and transmission of energy in the form of electromagnetic waves. Electromagnetic waves, they have an electric field component and a magnetic field component. They have, different types of electromagnetic radiation has different amounts of energy. We can see here a fairly low energy form of electromagnetic radiation. It has a long wavelength. And here is a fairly high energy form of electromagnetic radiation. It has a short wavelength, the distance between the crests of these waves. Now, we can see that the long wavelength form, it has a low frequency. You can see that there are not a lot of waves that might hit per second, whereas the short wavelength form, it has a high frequency. There are a lot of waves that hit per second. We can see that the wavelength and the frequency of electromagnetic radiation are inversely proportional. One wavelength might go down as we go from high to low wavelength, and when that occurs, the frequency goes up when we went from the low to the high frequency. We can see that wavelength times frequency is equal to a constant. Now, when we're dealing with light, the equation is the speed of light is equal to lambda, or our wavelength measured in meters, times nu, our frequency, which is measured in the number per second, or 1/2, or also known as hertz. Now, by the way, the speed of light is 3.00 times 10 to the 8 meters per second. Now, this is the same regardless of whether you're dealing with a high or low energy form of electromagnetic radiation. The speed is always the same as long as you're going through a vacuum. What are some different types of electromagnetic radiation? They all travel at the same speed, but they have different frequencies and energies. Now, I think it's best to kind of start in the forms of light that you're most used to, where we're talking about the visible spectrum. Here we have the visible spectrum, which is all these different colors of light. We have the fairly low energy visible form of light, red, which has a wavelength of 700 nanometers about, and this ranges to the highest energy form of visible light, violet light, which is about 380 nanometers in wavelength. Now, you can see Roy G. Biv here. Roy G. Biv. We have red, then we have orange, yellow, green, blue. I didn't have room for indigo here, and then violet. So this is kind of our starting point. But we could talk about infrared radiation. This is right by the red part of the visible spectrum. Infrared, you should know that's next to the red part. Now, infrared is known as IR. It has less energy than visible light, yet it's somewhat responsible for the transfer of heat. You can have infrared goggles and see at night certain animals, say, might be releasing heat by the red light that you can see with the goggles. We also have ultraviolet light. This is light which is shorter wavelength or higher frequency or higher energy than the violet light of the visible spectrum. You know that this form of light is responsible for getting tans and then later skin cancer. We kind of spend most of our time talking about these three forms of light: infrared, IR, visible, and ultraviolet, UV. But you should also be familiar with more energetic forms of light, like X-rays. You know they're more energetic because you have to be careful around them. We wear lead around our bodies if we're getting an X-ray at the dentist. X-rays are harmful to us because they have high energy. Gamma rays are also even more harmful to us. They come out of the sun or nuclear reactors. or explosions. Quite dangerous. They'll mess you up. And then less energetic than infrared, we have microwave, then we have radar, and then we have radio waves. Now, if you can remember kind of the varying amounts of energy or degrees to which these will mess you up, you'll be able to remember the relative frequencies and therefore wavelengths of these forms of light as well. Yes, these are all different forms of electromagnetic radiation. These are all different forms of light. It's just that most of these forms are not visible to us, to our eyes. All right, so yes, we saw that there's a relationship between frequency and energy. These high energy gamma rays have high frequencies. You see this because there are so many of them here, or there are such short wavelengths. Yes, high frequency means high energy. In fact, there's a direct relationship between these two. Energy is equal to Planck's constant times frequency, nu. Yes, frequency is in 1/seconds units, or hertz units, and Planck's constant, in order to be multiplied by that to give energy, is equal to joules times seconds. So that seconds cancels out, and joules is left over when you get energy. Yes, H is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Now, scrolling down here, we can do calculations about frequency and wavelength and energy. For example, a photon has a wavelength of 624 nanometers. Calculate its frequency and energy. All right, so you want to use this equation to solve for your frequency first. We have wavelength, lambda. We want to find frequency. And so manipulate this equation by dividing both sides by lambda, so that frequency, or nu, is speed of light over lambda, or wavelength. So plug in, your speed of light is 3.00 times 10 to the 8 meters per second, yet your wavelength currently is in nanometers. You can't just plug in nanometers into here. You need meters, so that meters will cancel out, and you'll be left with frequency, or 1/seconds. So we need to convert our 624 nanometers into meters. So you know that there are 10 to the 9 nanometers per meter. This gives you 6.24 times 10 to the negative 7 meters. That's the same as 624 nanometers. And if you don't have a fancy calculator to do this, you will need to break this calculation into two parts, where you have the regular numbers part, 624 divided by 1, and then, also call that 6.24 divided by 1. And then we have that 6.24 times 10 to the 2. That was 624. We have 10 to the 2 over 10 to the 9. That's our kind of scientifically notated part. So breaking it down into these two parts, we have 6.24 over 1, which is 6.24, and we have 10 to the 2 over 10 to the 9, or 10 to the 2 minus 9, which simplifies to 6.24 times 10 to the negative 7. Super. So now that we plug in our wavelength in meters, we're able to calculate now for our frequency. Again, if you don't have a fancy calculator, you need to break it down into two parts. 3 divided by 6.24, and 10 to the 8 divided by 10 to the negative 7. And 3 divided by 6.24 is 0.481, and 10 to the 8 divided by 10 to the negative 7 is 10 to the 8 minus 7. Or we have 0.481 times 10 to the 15. Or, to get into scientific notation, move the decimal once to the right, so that it's 4.81 times 10 to the 14. All right, now that we have our frequency in reciprocal seconds or hertz, we can find for our energy. Energy is equal to Planck's constant times frequency. Plug in your Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. Plug in your frequency, now 4.81 times 10 to the 14 reciprocal seconds, and you find that the energy is 31.9 times 10 to the negative 34 plus 14. Or it's 31.9 times 10 to the negative 20. Or, to get into scientific notation, move the decimal once to the left, and doing so, that moves your 10 to the negative 20 into 10 to the negative 19 going up the staircase. We get 3.19 times 10 to the negative 19 joules. This is the energy of an individual photon of this wavelength and energy. Thanks for watching, guys.